Imagine being stuck in a traffic jam inside a tunnel. We heard a big bang ahead of us, but we don't know why. Suddenly, we get a notification from our emergency app, which shows us the closest way to the emergency exit. What happened? The digital twin of our tunnel connected to the control center and reported a fire. It showed us the way to the closest exit.
Digital twins aim to simplify our lives. For example, a digital twin can monitor an entire tunnel, ensuring that equipment is regularly tested and replaced to prevent dangerous breakdowns. It can simulate emergencies like smoke spread and confirm that control systems function properly, ensuring safe evacuation even after years of use. They also reduce resource waste, adjusting energy consumption based on energy sources, grid usage and prices. Even in the case of extreme weather, a digital twin can simulate real-time events and suggest life-saving measures.
Most of us know about digital models. Those can range from 2D plan scans to the 3D geometry of buildings. Such models can also contain technical details such as materials and fire safety requirements. However, the connection between the digital model and the real object exists only in the minds of the planning team until the building is actually realized. The digital shadow, on the other hand, is no longer purely digital. It can be constructed step by step from the digital model as soon as the first parts of the real object are constructed and become reality. These parts can automatically transfer real data into the digital model, and this transforms it into a digital shadow of real objects that is cast into the digital world. As soon as the real object becomes controllable, we can go one step further. Now, we can delegate tasks to the digital shadow. For example, we can set the number of revolutions of the air supply fan. This allows us to describe the digital shadow as a digital twin. Now, it not only reproduces parts of the real world into the digital world, its actions can actually influence events in the real world.
Digital twins can be very diverse. Depending on the real object and on its digital twin's task, it requires different collaboration, data management and integration tools, and different analysis and modeling methods. For example, the digital twin that can be used to manage the emergency of smoke infiltration in a tunnel must contain a whole host of other models. A geometry model for computational fluid dynamics and a physics model to describe vehicle fires. In addition, it requires information on the tunnel systems and needs connections to the sensor, data transmission and control networks, as well as access to multiple analysis tools. But that is not all. We also have to answer a number of questions in advance. How detailed does the digital twin have to be? Who keeps it up to date? Who needs to understand it? Which technical guidelines must it conform to? Who creates which of its parts? To be able to manage all of this and maintain a good overview, we at TU Wien are developing a metamodel.
What exactly is a metamodel? Think of it like this. The relationship between a metamodel and a model is similar to that between a grammar and a sentence. The grammar provides the rules for constructing a sentence, just as a metamodel defines the structure of a valid model. However, to create meaning, a sentence also needs words from a dictionary. In the same way, a model requires technical terms from engineering practice to be useful. Engineering guidelines help provide these terms. Just as we can communicate effectively when we share grammar rules and word meanings, engineers can collaborate smoothly in the digital world if they follow the same metamodel and guidelines.
One challenge preventing wider use of digital twins is the high effort needed to create and maintain them. At TU Wien, we are working on methods to streamline this process by seamlessly integrating tools, data sources, sensors, and actuators using the metamodel. We are also developing tools that allow digital twins to be generated automatically from pre-designed building blocks. These blocks can be assembled to meet domain-specific requirements, reducing both the effort and the chances of errors. A good example is the digital twin for simulating smoke propagation in a tunnel. Previously, creating the simulation model, computational mesh for CFD analysis and sensor network integration could take several days. Now, much of this process can be automated.
Our goal is to simplify the creation and maintenance of digital twins. so it no longer feels like an overwhelming task for engineers. We also aim to guide decisions on whether a digital twin is needed, as unnecessary or inappropriate use can really waste resources. When used in the right way, digital twins can lead to significant improvements in our built environment.